Have you ever wondered what's really inside a physicist's toolbox? It's not just lasers and lab coats. At its core, it's a set of incredibly powerful mathematical ideas. And today, we're going to open up that toolkit and see what's inside, the essential math that lets us describe everything from a planet's orbit to the electricity flowing through your walls. This right here, this quote, just gets to the heart of it all, doesn't it? A good physics question is a good math question. It really suggests that to understand how the universe works, you first have to learn how to speak its language. And yeah, you guessed it, that language is math. Okay, so that brings us to the big question. There's a whole universe of mathematical concepts out there. So which ones are the absolute, non-negotiable must-haves for a physicist? Well, that's exactly what we're going to figure out. Let's start building that toolkit one piece at a time. First things first, our initial set of tools is all about describing the world as if we've hit the pause button, like a snapshot in time. See, before anything can move, we have to know how to describe its shape, its position, where it is in space. You can think of this as the fundamental blueprint of reality. The very first tool we're going to pull out of the box is trigonometry. Now, I know it might seem like it's just about triangles, but here's the secret. Pretty much any complex shape or force can be broken down into a bunch of simple triangles. That makes it the physicist's universal ruler and protractor for measuring, well, everything. And here's where it gets super practical. Let me tell you, physicists absolutely love a good shortcut. And the 3-4-5 triangle is a total classic. If you see a right triangle and its sides are 3 and 4, you instantly know the long side, the hypotenuse, is 5. And even better, you know the angles are roughly 37 and 53 degrees. No calculator needed, no fuss. It's a massive time saver. All right, moving beyond just triangles, physicists need to see the bigger picture. And that's where graphs come in. An equation, like the one for a straight line or a curve, isn't just some abstract algebra problem. No, it's a visual story. It shows you exactly how one thing, say distance, changes as another thing, like time, moves forward. These are literally the shapes of the laws of physics. Okay, so we've got our blueprint for a static world. But let's be real, the universe is anything but static, right? It's always in motion. So to describe that, our toolkit needs a serious upgrade. We don't just need a blueprint anymore, we need an engine. So how do we even talk about change? Well, think about a road trip. You can talk about your average speed for the whole 2-hour drive, but then there's your instantaneous speed, the exact number on the speedometer at the precise moment you glance down. One's a general summary, the other is a perfect snapshot in time. And the amazing tool that lets us find that exact instantaneous change, it's called differentiation. You can think of it as a physicist's super-powered microscope for looking at motion. It lets us zoom in on any single moment and ask, how fast is this thing changing right now? And this is where it just gets so powerful. You use differentiation on position over time, you get velocity. You do it again on velocity, you get acceleration. In the worlds of electricity, you look at the rate that charge is flowing, boom, that's electric current. This one single tool unlocks some of the most basic and crucial concepts in all of physics. It's incredible.
But of course, what happens when things get more complicated? When one change actually depends on another change. That's where a handy little technique called the chain rule comes in. It's just a systematic way to untangle these kinds of nested problems. You just deal with the outside function first, then the inside one, and then multiply them together. It's the key to handling really complex systems.
So once we can measure change, we can do something even more amazing. We can find the exact points where that change, well, where it temporarily stops. This is the secret to finding maximums and minimums, the absolute extremes of a system. It's how physicists optimize things and predict what's going to happen. Just think about it for a second. How do you find the perfect angle to launch something so it goes the farthest distance possible? Or how do you figure out the shape of a molecule that uses the absolute minimum amount of energy? These are all optimization problems, and they pop up everywhere in physics. The big insight here is actually really simple, and it's visual. Just picture throwing a ball up in the air. At the very, very top of its arc, for just a split second, it stops going up, but it hasn't started coming down yet. Its vertical speed, its rate of change, is 0. And on a graph, that's the point where the curve is totally perfectly flat. The slope is 0. And that simple observation is the whole trick. Since we know from before that the derivative is the slope at any point, all a physicist has to do is take the derivative of a function, set it equal to 0, and solve.
The answer tells you exactly where those crucial peaks and valleys are. It's that elegant.
Okay, so we figured out how to describe space, and we've learned how to break motion down into these infinitely small little moments. But what if we need to do the exact opposite? What if we need to add up all those infinite tiny pieces to finally see the whole picture? For that, we need our final tool. And that final tool is called integration. So if differentiation is like analysis, breaking things down into smaller parts, then integration is synthesis. It's all about building them back up. It is the mathematical process of summing up an infinite number of tiny, tiny pieces to find out what you get when they're all put together. Now, on a graph, integration has a very clear visual meaning. It's the total area under a curve. But you might be thinking, why on earth does that matter? Well, because in physics, that area isn't just some abstract shape on a page. No, it can represent real, tangible things, like the total distance a car has traveled, or the total amount of work a force has done.
And there we have it. We've gone on a journey through this mathematical landscape, and we've assembled the essential pieces of the physicist toolkit. So let's just lay them all out on the workbench one last time and see what we've got.
So we started with trigonometry to draw the blueprint of space and angles. Then we used graphs to actually see the relationships between things. We brought in differentiation to analyze change at any given instant. We use that tool to find maxima and minima, which lets us find the best possible outcomes. And finally, we used integration to put all those tiny pieces back together and see the big picture. So this whole journey leaves us with a really deep question, Is the universe itself actually built out of math? Or is math just the most effective language that we humans have come up with to describe it? It's a huge question and definitely something to think about. Thanks so much for joining me.